Example, investigating swirl and tumble flow with a comparison of techniques. Computational fluid dynamics is the engineering discipline of trying to predict fluid flow behavior, fluid motion as it interacts with geometries like cars, ships, or airplanes. If we want to understand how fluid will interact with a surface, one way to do is to build an actual surface and build a flow environment and to visualize the flow with smoke or dye or other substances. This is something fluid engineers do. This is a field of engineering. But it is very expensive. Just try a test flight and then attempt to visualize the airflow around the wings with smoke. This is a very expensive experiment. There are analog solutions. Can we come up with a digital solution that makes this investigation more feasible to accelerate the engineering and make it less expensive? That is the inspiration behind computational fluid dynamics, CFD. Here's an example of combustion chamber in an automobile engine. The engineer's goal is to obtain a perfect mixture of fuel to air. The way the engineers propose to do that is to create this helical motion inside the combustion chamber, left, and for the diesel engine example, the ideal pattern for the mixture of fluid flow is a tumble motion about an imaginary axis pointing out from the page, right. Investigating swirl and tumble flow with a comparison of flow visualization techniques. Image courtesy of Larame et al. We can build a real physical solution, but it saves time and money to go through a digital process first before we build real solutions. We do not need to build as many real solutions. The digital solution is computational fluid dynamics. As we know in computational fluid dynamics, the number one challenge is the amount of data that simulations generate, which is at the gigabyte and terabyte scale. CFD simulations run from weeks to even months, even on high-performance computing machines. How can we use visualization to make sense of this massive amount of CFD data? Let's look at some data visualization solutions for CFD data, visualizing the swirl and tumble motion. See? This is the tumble motion example, so those are called path or short path lines in the flow direction, and the color is mapped to crank angle. We have a piston head moving up and down 1,000 cycles per minute, at the bottom, not shown. Pathleets visualizing tumble motion of flow. Image courtesy of Garth et al. We can also use vortex core lines, a combination of these green paths of vortex core lines, centers of swirling flow. See? When combined with particles, the particles show flow behavior around the vortex cores. This is what we call feature-based flow visualization, looking for special features in the flow. We can visualize the flow at the surface itself using so-called critical points. That's a sink and that's a saddle point. And then there are some curves that connect the different points. Those are special kind of streamline called separatrices, and they show the topology of flow. A hybrid visualization of particles and vortex core lines. Particles swirling around vortex cores aid the visualization of vortex core strength. Image courtesy of Garth et al. Topology is a skeletal representation of the flow. We can see the time-dependent topology of the flow sinks, the sources, and the vortex core lines. The vortex core lines are tubes in the middle. We also see a separatrix on the boundaries of the surface, and they are animated over time. That's a slow motion version of time. It is slowed down quite a lot. In reality, this is inside of the engine and it's moving up and down hundreds of times per minute. We can also use a volume visualization of the fluid flow specifically for the vortices, so the vortices are the areas of swirling motion. The red is mapped to one direction of circular flow and blue the other. The idea is to visualize the swirl and tumble motion. In this case, the tumble motion is about an imaginary axis that points out at the viewer, just like a tumble dryer. We can observe an axis pointing out and downwards to the left of the ideal axis. It's a very unstable axis of rotation. That is what these visualizations show, an unstable rotational axis. The computation fluid dynamicists see this and they observe this is not the ideal tumble motion. There's a little bit of tumble motion right around the perimeter of the geometry, but as soon as we look in the center we still see some swirling motion, but it's very far from the ideal kind of tumble motion they strive for. They have to make some modifications to the geometry to try to realize the best mixing possible. And here this is also not the ideal swirl motion. The motion is off-center. Again, they have not achieved their target of the ideal motion. That's what these visualizations show. They show the difference between the actual and predicted motion. One of the things that the engineers like to know is where precisely the flow is misbehaving. They know what they want to see and what they expect to see. They like to see visualizations that highlight unwanted behavior. That's what all users want to see. In fact, that could be in the knowledge evolution pipeline. One of the things QPC would like to see where the abandoned calls are and when people are not behaving properly. Here the engineers can see where the flow does not behave properly. This is one of the strengths of visualization, to show when and where behavior go wrong.